Swayamprabha. Digital India. Educated India.
Greetings, and it's my pleasure to welcome you again to this course on CFD. This is the last module for this week. In this module, we will take example problem of flow in a lid driven cavity and explain step by step steps involved in CFD, discretization procedure, corresponding display of a working code. In the last module, we are going to complete this procedure, and in addition we are also going to see different post processing and corresponding display of code. Steps involved in doing the simulation of flow in a lid driven cavity are listed here. We already mentioned about this in other modules as well. Hence, the fifth step is the one that we are going to see particularly in this module. Fifth step is project the intermediate velocity onto a divergence free space using the pressure calculated in the projection step. So, this particular step is otherwise also called correction step. Then you repeat this process until the solution has reached the convergence condition. Once you obtain the velocity field, then you do post processing to get different information about the flow. So, in the projection step method, we have already seen predictor step, solving the pressure Poisson equation to get pressure everywhere. Using this pressure computed in the pressure Poisson equation, the intermediate velocity which are calculated without considering the pressure term, and they are also referred as u star v star. These two velocities are projected onto a divergence free space using the fractional step algorithm, and this particular step is called correction step, and it is listed here. So, u at n plus 1, that is a new velocity, equal to u star minus delta t into del p. Similarly, for v star as well, and if you discretize the above equation for u as well as v velocity, then we have as shown here, that is u at I comma j, new value at n plus 1 equal to u I comma j star minus delta t p I plus 1 comma j minus p I comma j by delta x. Similarly, for v, so v at I comma j n plus 1, that is a new value, equal to v I comma j star, that is the intermediate velocity at the same I comma j location, minus delta t p I comma j plus 1 minus p I comma j by delta y. We will see the corresponding code here. So, function u v, projection step I max, j max, dt, dx, dy, u star, v star, p velocity. Then u is already initialized, v is also initialized with the corresponding number of required array size. So, for u it is I max comma j max plus 1, and for v it is I max plus 1 comma j max. Now, we do the projecting the intermediate velocity onto the divergence free vector space. First, for u velocity, that is what these lines are for. So, for I equal to 2 to I max minus 1, and for j 2 to j max, u I comma j equal to u star I comma j minus p I plus 1 comma j minus p I j into delta t by delta x. In the form of code, it is into dt by dx. These are same as what we have seen in the previous slide in the form of equation. Similarly, now for the v velocity, so for I 2 to I max and for j 2 to j max minus 1, v I comma j equal to v star I comma j minus p I comma j plus 1 minus p I comma j multiplying by dt by dy. And what is shown here is a complete listing of outer loop code. So, you start from here, the right pressure Poisson coefficient matrix. So, AP equal to get coefficient matrix I max comma j max comma dx comma dy. Then outer loop iteration time is equal to 0, which is you start the iteration by initializing time. So, first it is time is equal to 0, then for I equal to 1 to iteration, that is number of iteration you can decide, or the convergence criteria you can decide. So, time is equal to time plus dt, which is also defined, u star comma old u equal to u momentum and corresponding argument. Similarly, v star comma old v equal to v momentum corresponding arguments. So, these two lines represent solving the u momentum equation for respective velocity, that is u star and v star. Then we know pressure Poisson equation has right side term and left side term. So, this BP is calculating the right side term of the pressure Poisson equation. We have seen them independently in detail in previous modules. What you are seeing here is a complete listing of the outer loop. So, BP equal to get RHS I max comma j max comma dt comma dx comma du comma dy comma u star and v star. So, this line calculate the RHS vector of pressure Poisson matrix. Then you solve the pressure Poisson equation, and that is what is shown here. Then you project the step, this we have just now seen, to get u and v. Once you get u and v at the new time level, after the final correction step, you calculate for the divergence and Courant number. So, divergence comma Cn, Cn represent Courant number, and there is a separate argument for that. So, divergence div Cn I max j max dt dx dy u v. So, you can decide if the number of iteration is more than the desired number of iteration, or you can decide based on the Courant criteria. So, C max is a maximum iteration. So, converge u comma old u, and you can also have some display on the screen for checking the progress of the code. So, display, so it will display this particular lines will display iteration number, Courant number and maximum value. If the convergence maximum is less than the error that you have specified, then it will break, otherwise it will continue, and you have final display again. So, once you get solution, then we have to do post processing. There are various methods available for post processing. You can look at u, v, these are two velocities listed in this 2-dimensional simulation. You can look at u and v at every node. You can also look at pressure at every node. You can also look at u and v in different form, for example, stream function, vorticity contour, and these are listed here. So, you can have a contours of velocity, you can have a stream function contours, vorticity contours, center line velocity, you can have a velocity line plotted at any specific x and y grid line, then you can have a contours of pressure, etc. So, plotting the contours of velocity, pressure and center line velocities are straightforward. Obtaining the stream function and vorticity values from the velocity values are explained in the subsequent slides. So, this is the example problem we had, that is flow in a lid driven cavity, and this particular slide will try to see what is known as a center line velocity. So, this line that is shown here corresponds to x at half of this length. Please recall, we defined the coordinate along this horizontal line is x coordinate line and along this vertical line is a y coordinate line. So, at the center of this face you have a line marked, and we are going to see velocity plotted along this line, and that is what is shown here. And we mentioned in one of the beginning lectures, we have what is known as a non-dimensionalization. So, u, that is a local velocity, is non-dimensionalized with the driving velocity. The driving velocity is a velocity scale, and for this problem we have taken driving velocity to be 1. If you non-dimensionalize any velocity by driving velocity, then you get u by u, and that is what is plotted on the y axis, and the length of the cylinder, length of the cavity, in this case it is square, and that is taken as L, and that is used to non-dimensionalize the distance. So, we are going to plot along this line that is marked, and this is in y direction, and that is non-dimensionalized with the length. So, you have y over L going from 0 to 1. So, 0 is on this side and 1 is on the other side. We mentioned we have a boundary condition, that is u is equal to 1. So, at y by L equal to 1, you have the maximum velocity, because it is non-dimensionalized, you have u by u to be 1. And on this side, that is on the bottom, you have a wall and you have a velocity boundary condition, no slip condition, u is equal to 0. So, you have u equal to 0 at this point, and it goes down to some negative value at particular value of y by L, then it starts showing positive value. That is the interpretation of this line. It is also possible to plot velocity variation along any particular location, both horizontally as well as vertically. And you can also look at velocity in the form of a contour. So, what is shown here is a u velocity contour. So, this gives you variation of velocity for the entire domain in whole. So, this red color corresponds to maximum velocity, and each line corresponds to one particular value. So, along this contour line velocity values remains the same, and this blue color corresponds to very low velocity, and that is interpretation of this contour plot. You can also look at pressure in the form of a contour, and that is what is shown here again for the entire domain, and you plot contour along with legend, and that is what is shown here in the form of a color bar. So, you can interpret this red color corresponds to the value 60, and this blue color corresponds to value minus 60, and this picture tells us that the flow is symmetric, and that is why you get symmetric pressure contour. Next is a stream function contour. We know the definition of stream function relating to velocity. So, u equal to dou psi by dou y and v equal to minus dou psi by dou x. You employ the above definition. So, to get stream function relating to velocity, for now we take any you can take any velocity. For now we take v velocity. So, v I comma j equal to minus psi I plus 1 comma j minus psi at I comma j by delta x. Please remember, streamlines are contours of constant stream function, and what we have done here is a discretized form of this particular equation. So, you define any particular line as a reference psi given a value of 0, then you can go on integrate based on this velocity and this delta x to get psi at I plus 1. So, psi at I plus 1 comma j equal to psi at I comma j minus v I j into delta x. Steam function is calculated using the above relation, and you have a corresponding display of the code shown here. So, function psi equal to steam function I max comma j max comma dx comma dy comma u and v, and psi or initialize beginning zeros I max comma j max, and for I 2 to I max minus 1 psi I comma 2 to j max minus 1 equal to psi I minus 1 comma 2 to j max minus 1 minus dx into v at I comma 2 to j max minus 1. This line is same as what we have seen in the previous slide. It calculates for all I location. Then once you get the value of psi, you can look at the contour as shown here. Again there is a corresponding color definition in the form of a legend shown here. So, color map and corresponding color values indication is also given here. So, the square cavity, so y is going from 1 to y is going from 0 to 1 and x is going from 0 to 1, and at the center you have a very low value, at this point you have a very low value, and you have a contours connecting all constant value of psi, and this is the meaning of steam function contour. Next we have a vorticity contour. So, vorticity again defined based on velocity component as shown here. Omega is equal to dou v by dou x minus dou e by dou y, and you employ the above definition, write the discretized form of that equation. Omega at I comma j equal to v at I plus 1 comma j minus v at I comma j by delta x minus u at I comma j plus 1 minus u I comma j by delta y. So, using this you can calculate the vorticity, and it is shown in the form of a code. So, we have function omega, that is a separate subroutine or function to calculate omega, and you define corresponding arguments of vorticity I max comma j max comma dx comma dy comma u comma v. So, you give velocity fields u v, you give delta x delta y and I max j max to the function, it will give you the vorticity. As usual, you initialize the omega array, then you calculate omega as shown here. So, for I equal to 1 to I max and for j equal to 1 to j max, omega at I comma j equal to based on velocity component v and based on velocity component u, and this is again a code written corresponding to the mathematical definition we had in the previous slide, and you also define at specific location. So, omega 1 comma 1 is defined as shown here, omega 1 comma j max and omega I max comma 1 and omega I max comma j max. So, these are values of omega at boundary condition locations, and once you get omega, again you can look at the flow through omega in the form of vorticity contour as shown here. Again you can have an interpretation, color and then corresponding values are given here. So, you can have idea where is the maximum omega and where is the minimum omega. So, a complete flow chart for this problem is given here. The first step we have the grid generation, second step discretization of the governing equation, third step you solve momentum equation to obtain intermediate velocities. We have separately u and v momentum equation, you can solve them separately. Once you get u star and v star, then we get pressure Poisson equation and we solve the pressure Poisson equation again separately. Then this intermediate velocities obtained are corrected by this projection step on the divergence free space. Once you get correct velocities, then they are post processed to get results and to look into the flow. Complete listing of the code is given. We have seen the code part by part. Now, we will see the entire code. Navier-Stokes equation, explicit formulation, lid driven cavity flow. The code is based on the projection step method proposed by Coring. So, we have all these initial lines, then you define grid size and other parameters. I runs along x direction, j runs along y direction, Reynolds number is defined and that is used symbol Re, dx comma dy are cell sizes along x and y direction, dt is a time step value, velocity is a lid velocity, that is a boundary condition on the top wall. So, these are comments written. Again we have explained in the beginning, grid we are using only 4, but to get good results we have actually changed the grid to 33, that is why you see here I max 33, grid size in x direction. Similarly, j max equal to 33, grid size in y direction. So, we set the limit of iteration to be 20,000 and convergence criteria, that is error in the divergence, as 1 10 to the power of minus 4, Reynolds number as 1 and velocity boundary condition on the top wall as 1. So, once you define number of grid lines, then you calculate dx and dy, and that is what is shown here, dx equal to 1 upon I max minus 1 and dy equal to 1 upon j max minus 1. So, x is going from 0 by delta x value up to the value of 1.0. Similarly, y is going from 0 to 1 with the step value of dy. dt equal to 0.0002, and you have a complete listing of the code. We have already seen part by part. So, this is the first line is for the pressure Poisson coefficient matrix, then you have the outer loop, time spent, then the iteration starts. So, we calculate separately u momentum, v momentum, and this line corresponds to right side vector of the pressure Poisson matrix. Then you solve the pressure Poisson equation, you get solution for pressure, then you do the projection step to get the correct u and v velocity, check for divergence and also check Courant number. Then you check whether it is within number of iteration and within Courant number, and then you break or you continue. Then finally, you can have a list of display. So, number of iteration, total iteration, Courant number, etc. And this same, now we have included the post processing lines also. We have stream function and we have omega, and finally, you can also plot results. This is a complete working code using MATLAB. We have explained the algorithm and corresponding code part in detail. Now, we will put entire algorithm and then we will explain how the code is actually running and also discuss the results uptime. What is shown here is a MATLAB code in MATLAB platform itself. Now, let us start seeing looking at the lines, Navier-Stokes equation, explicit formulation, lid driven cavity flow, these are certain comments. Then we have clear screen. First one, we start talking about grid. We explain initially with the 4 by 4, to actual running of the code we ran with 33 by 33. So, I max is 33 and j max is 33, number of iteration allowed is about 20,000, and for convergence criteria we set the limit 10 to the power of minus 4, Reynolds number is 1 and lid driven velocity condition is 1. Then we define grid based on this. So, dx equal to 1 upon I max minus 1 and dy equal to 1 upon j max minus 1, and dt is also set as 0.0002. Then we do the memory allocation of all the variables. So, pressure, then RHS side of the pressure equation, then divergence calculation, vertical velocity, in that we have predicted velocity v star, then actual velocity. Similarly, for horizontal velocity u star u, Then boundary condition u star, we define boundary condition for u star as shown here. Then velocity on the collocated mesh, this is required, we solve equations or we store variables at staggered location. Once we obtain solution, then we need to do post processing. To enable post processing, we convert the variable from staggered grid to collocated grid arrangement, and that is done using this collocated definition of the variables. Then we solve pressure Poisson equation. Now comes outer loop. So, we have u star, u momentum, and that is given in detail in this particular function. We have seen all this in detail. Convective term again initialized, alpha is a common factor that is also defined. Then we calculate for convection term u at different location, and that is what is shown here, u east, u west, u north, u south, similarly v north and v south. Finally, you calculate convective term. Then you compute fractional step velocity including convection term as well as diffusion term as shown here, and that will be u star because we have neglected pressure in the first step. Once you calculate u star, we need to apply boundary condition and corresponding lines are shown here. We come back to main code. So, we explain u momentum, similar steps are there in v momentum function also, that is again displayed here separately. V star equal to convection term and diffusion term. Once you find V star, apply the boundary condition as shown here. Come back to main. So, we have u momentum, V momentum explained, then pressure Poisson equation, get the right side of the pressure Poisson equation first, that is in the module get RHS. Again go to that particular module and it is shown here, initialize, then calculate all the coefficient values of the right side matrix. Go to the main, then you solve the pressure Poisson equation, press Poisson is the corresponding module, go to the press Poisson dot m. So, we have initialized pressure, then F RHS vector of the pressure Poisson equation, then we define pinning of the pressure because we are interested only the pressure difference, and one point is pinned to 0 and all other values are referred with respect to that pinned point, and that is what is this particular line. Then we solve the matrix, and this is a inbuilt matrix inversion procedure. So, pressure is obtained. So, once you obtain pressure, then you apply boundary condition. So, left side, right side, bottom wall and top wall. Again go to the main. So, we have done now pressure Poisson equation, we got pressure, then this pressure is projected to get the corrected velocity, and that is what is done in this module projection step. So, we go to the projection step module. So, again values are initialized, zeros for u and v, then you correct the velocity. So, u star was initially obtained, and the pressure is obtained from pressure Poisson equation. Using these two, you get the correct velocity, the expression as shown here. Then once you get u, then we need to ensure boundary condition, that is also done using these lines for left boundary, right boundary, bottom wall and top wall. Similarly, for V equation, so V star is used and pressure, corrected pressure is used. So, to get correct velocity, once you get correct second component of velocity V, apply boundary condition for V, and that is done by these lines. Go back to the main. So, we have done pressure Poisson projection step to get correct u and v velocity. Now, we need to check whether divergence is satisfied. So, we have a separate module div Cn, let us go to that module. So, in div Cn we calculate the continuity error. So, this is dou u by dou x and dou v by dou y. Then you calculate also the Courant number, it is helpful. So, you calculate Courant number based on this expression here. Come back to the main. So, we calculate divergence, then we calculate Coulomb number, then we calculate converge next. So, go to the converge, this finds out the absolute error and find the maximum of absolute error separately for u velocity and v velocity, and these are lines here, and you find the maximum of these two, and that is what is attributed here as a C max. So, come back to the main. So, C max is compared against